Now we're going to move on to the second part of kinetics, which is calculating the rate law and then calculating the half-life of a reaction. So rate law, let's talk a little bit about the rate law. And what you'll remember from what we've done so far is that the rate of reaction is dependent on the concentration of the reactants. In the rate law, we kind of get a little bit more specific about that. We talk about how really is it dependent, how the rate of the reaction is really dependent on the concentration of reactants, or does it really matter? Does the concentration of reactants really matter? So for that reason, we need to do some experimental work. This is all done in the lab, and then this is what we come up with. So for example, if you have a reaction like this, which is A, B, C, giving you D and E, then the rate law can be expressed as rate is equal to K, which is a constant, and then A, B, C are the concentrations of the starting material, and then X, Y, Z are the powers that these concentrations are raised to. Now, if you notice the small a, b, and c, which are the coefficients of the reaction, they are not in this rate law at all. And that's because they don't matter. Okay, and so what does matter is the x, y, z, and these things are calculated experimentally. Also, the K over here is what we call a rate constant. The rate constant is going to be specific for a reaction, also at a particular temperature. As we go on to learn more and more about the kinetics, you will see that the rate is dependent on a number of things. So K here, which is the rate constant, is very specific for the reaction and for the temperature. X, Y, Z generally are going to be integers, which means that they're not going to be fractions or decimal points, or in any case, in any of those. It'll be 0, 1, 2, 3, 4 or something like that. And they have to be calculated experimentally. There is no way that you can look at a reaction and say, this is going to be the rate law for this reaction, okay? Which means that you're trying to predict the value of X, Y, Z just by looking at a reaction. That's not going to happen, okay? X is called the order at which A will change, then Y is the order at which B is going to change, and then Z is for C. So you can have any number of reactants. If you just have one, then you only have X or Y, whatever it is. And then if you have two reactants only, then of course you just have the two orders over here. So these will let you know how the concentration is affecting the rate of the reaction. And this is called the order of reaction in a way, okay? And so this is based on individual concentrations, and then if you add all of these orders up, the X, Y, Z, that's going to give you the overall order of reaction, okay? So you can find the order of reaction with respect to A, with respect to B, and with respect to C, and then the overall order of reaction. K, by the way, is also calculated like this. Okay, so once you have figured out the order of reaction, then once you know the K, the rate of reaction, then you can calculate for K for that particular reaction at that particular temperature. So the orders of reaction, there are three different ones that we're going to study. You can have more, but usually you will find almost all the reactions to be either zero order, first or second order. So what does this mean? Okay, and remember these orders are going to be the integers that are going to be on top over here. So if it's a zero order reaction, it means that you can change the concentration of the reactant and it does not affect the rate of reaction. So you can have it less or more, and it does not change the rate of the reaction, okay? Whereas previously we had learned that the concentration of the reactants affects the rate of reaction, but if it's zero order, it does not. All of this thing is going to come to play later on when we talk about the mechanism of the reaction, okay? All right, so first order reaction is when the rate is directly proportional to the concentration. And what that means is that if you double the concentration, you also double the rate of reaction. Okay, so that would be a first order. A second order of reaction is an exponential relationship, which means that if you double the concentration, you quadruple the rate of reaction. Okay, so you can have any of these orders, and again, you can't figure this out by guesswork. You have to calculate this. And then if you do the sum of the exponents, then you get the overall order of reaction. So for example, let's look at this reaction. Random reaction between nitrogen dioxide and fluorine to give this compound, and it was determined that the rate is equal to K, and then with the concentration of NO2 and then concentration of F2. Now you don't see any integers over here, and because they're not, it means that they are 1. If F2 was 0, I can either write 0 over here or not write fluorine at all. Okay, so either one would work, but in the reaction you can see fluorine is there, but if you don't see in the rate law, it means that fluorine does not affect the rate of reaction, or it is 0 order according to fluorine. So this is then the rate law for this, which means that changing the concentration of NO2 will change the rate of reaction, and changing the concentration of fluorine will also change the rate of reaction. Okay, so if you double this, you double the rate of reaction. You double this, you double the rate of reaction. So there's 1 and 1 for both, which means that the overall order is going to be 2, which is 1 and 1, which makes sense because if you're doubling both of them, then you should double the overall, okay, rate of reaction. You quadruple, okay, the overall rate of reaction. So that's how the order of reactions work, okay? That's what they mean. Now we're going to learn how to calculate these. To calculate the order of reaction, you have to do a series of reactions. You just can't do one, you have to do series of reactions. Depending on the number of reactants, you will have to keep one of them constant and change the concentration of the other to observe what happens. Okay, so if you have just 2 reactants, you keep one of them constant, double the other one, and then keep the other one constant and double the first one, and then see if there's any change in the rate of reaction. So that is kind of how this one works. Once you obtain the data, then you calculate the order of reaction, and then you can calculate K also from there. So for example, here's the reaction again between fluorine and, now in this case, chlorine dioxide. So if you have this, this is how you take the data, all right? And what you should be looking for as soon as you see a table like this is, okay, I got fluorine and I have these 2 constant over here, which means that these 2 should be changing, which they are. And then for the chlorine dioxide, I should have 2 reactions that are constant, okay? And then the fluorine should be changing, and that is happening as well. Okay, and so then you look at the rate of reactions, and the rate of reactions are different for everything, so which means that everything that you change is affecting the rate of reaction. Okay, so how you calculate the order of reaction is by comparing one thing at a time. Okay, so for example, you calculate for 1 and 2, experiment 1 and 2, where fluorine is constant and the chlorine dioxide is being changed, because you can see that as the concentration was changed, the rate also changed. If the rate had not changed, that means that it would be 0 order, okay, because the rate should not change if it's 0 order. All right, so if the concentration has changed and the rate is changing, that means we have to do some calculations. So here are the calculations. So here is ClO2, and these 2 numbers over here indicate that we're looking at experiment 2 over experiment 1 data. It has nothing to do with anything else. And so here are the molarities, which is the concentration. So 0.04 over 0.01 comes out to be 4. And then you do the same thing with the rate. Again, experiment 2 over experiment 1 rate, and you come out with 4 as well, which means that if you change the concentration 4 times, you change the rate also 4 times, which means it's a direct relationship. If it's a direct relationship, it's a first order reaction. So which means changing the concentration of ClO2 also change the rate of reaction directly. So first order with respect to ClO2. Now what we're going to do is we're going to keep the chlorine dioxide constant and see what happens with fluorine. Okay, so experiment 1 and 3, where chlorine dioxide is now constant and we're changing fluorine. So you do the same thing, and now you have experiments 3 and 1. So always keep the larger number on the top. It will make your calculations easy, because all we're looking for is the ratios. So if you keep the larger number on the top, your calculation, as I said, is easy. Okay, so then again, rate 3 over rate 1, experimental data, and it's 2 is to 2, which means that, again, there is a direct relationship, which means it's a first order reaction also with respect to fluorine. Now, if it was a second order, this would be 2, this would be 2, and this could be 4, or vice versa, okay? Or excuse me, this would be 2 and this would be 4. Okay, so which means that you would have to raise 2 to the power of 2 to get 4. And so raised 2 to the power of 2 means that that would be a second order. okay, if it was. But this is first order because you're getting the same ratio numbers. So then this is our equation, okay? When we write the rate law, this is the rate law. Rate is equal to K and then F2 and then ClO2. You can write 1, 1. You don't have to. I would advise that you do, okay? So that it gives you a sort of a frame of mind that, you know, you have to write these things out. And then, of course, depending on what the question is asking you, if you're supposed to calculate K, go ahead and calculate K. So rate divided by the concentrations of fluorine and fluorine dioxide will give you these things. Now remember over here, rate is molarity over seconds, and then F2 and ClO2, both of these are molar concentration, so that's molarity and molarity. So the units for K are going to be very specific, okay? So you have 1 molarity left over, and then you have the seconds also at the bottom which are left over. So it's per mole, per molar per second, okay? And those units of order of reaction are also specific. So keep that in mind when you're doing this. So obviously you can see that the value of K is going to be different depending on the order of reaction. For us, it was 1:1 over here. If it was 2, then we would have to square the concentration of fluorine, for example. Okay, we'd also have to square the units, okay, in that case. So this is how you would get any kind of a question for order of reaction. Let's look at another one, and we'll try and do this without doing much calculation. So if we can avoid it, why not? Okay, so here we have 3 experiments, and we have the concentration of A and B. So we have 2 random reactants, and then we are also given the rate of reactions. The first thing I do when I look at my rates of reactions is that all of them are changing. None of them are constant, okay, over here, which means that I probably have to do calculations for everything. So then looking at A over here, experiment 1 and 2, okay, over here. So, or looking at B. Looking at B here, B is constant for experiment 1 and 2. So if you have B constant and you're doubling the concentration of A, and the rate also doubles. 4.2 divided by 2.1 is 2. So this is 2 and this is 2. So which means that it is first order. You do the same thing for B, which means you keep A constant and then you look at the change in the constant rate of reaction. So in experiment 1 and 3, A is constant and you're doubling B. And so what happens to the rate here? The rate here is now 8.4 divided by 2.1. 2.1, that is going to give us 4. Okay, so which means that you have a quadruple rate of reaction going on over here. So which means that the reaction order is going to be second order, okay, with respect to B. So which means if you double the concentration of B, you quadruple the rate of reaction. Okay, so then our rate law is then rate is equal to K, first order with respect to A, and then second order with respect to B. Overall order is going to be third order. And then this is how you would calculate for K if you needed to. So the rate over A and then B square concentrations, and you pick any rate, it doesn't matter. Just pick any experiment, 1, 2, or 3, it doesn't matter. Just pick one set of data and then calculate for the value of K. Now, see here, the units are going to be different, okay, because now what we have is squared molarity, so our units are different. So a little bit about the units, because this does become important, and if you want, you can write this for yourself in a table eventually, is that for a 0 order of reaction, the unit of K is going to be molarity per second, okay? Or you can look at moles per liter also if you wanted to, but molarity will be sufficient because most of the concentration units that we'll be talking about is going to be molarity. For a first order reaction, the unit is going to be 1 over second, okay, which is per second. For second order reaction, which we did in the first problem, it's going to be 1 over molarity in second, okay, so per molar per second. If you know the units of K, then you can determine what the overall order of reaction is. You can't determine specifically for one reactant, but overall rate of reaction, then you can figure out, okay, if you remember your units. One of the other aspects about determining the rate law is that you can figure out how the concentration of the reactant is going to change over time. So once you know the rate law and the order of reaction, then you have to do a little bit more work, of course. Okay, there's always a little bit more work involved. And so you can calculate the concentrations, okay, over a given period of time, whether it's 10 seconds or 4 hours, whatever it is that you want to find out. So when you have to find out something over a period of time, for that, the best thing to do is calculus. Okay, and so using calculus, you can figure out what we call these integrated rate laws. Okay, and integrated rate laws are at time 0 and at time t. Okay, so where you have initial rate of concentration or initial concentration and then concentration at time t. Okay, so this is done by a series of derivations. Okay, and once you do all of that, then you get these equations. Now, I'm not going to have you do these equations, but I'm going to have you figure out which one to use when. So I'm not going to tell you that this is 0 order or first order. You're just going to have to figure that out yourself, okay? And then see how you can use these in doing the calculations. So at least you're not doing the calculus part, okay? So, or maybe I'll see, okay? We'll make things a little easier. But anyhow, if you have a 0 order reaction, then the rate law, where rate is equal to K, all right? And then remember, in case of 0 order, there is no dependence on the concentration of reactants, okay, at all. So in that case, this is the integrated rate law, okay, where the final rate, final concentration of whatever reactant you have is equal to minus Kt plus, and then you have the initial concentration. For a first order, where the rate is dependent on one of the reactants, then this is going to be a rate law. And then if you have a second order, where you have either two reactants or one of them, okay, which is to second order, then this is what your equation is going to look like. Now, again, as I said, I'll give this to you on the test. You don't have to memorize this, but you have to know how to use them. Let's look at an example for the for calculation of concentration over time. So cyclopropane is used as an anesthetic. The isomerization of cyclopropane to propene has a rate constant of 9.2 per second. If an initial sample of cyclopropane has a concentration of 6, what will be the cyclopropane concentration after 1 second? Okay, so initially it's 6, A0 is 6, time for us is 1 second. So what is the final concentration? That's what the question is. K is given to us. K is 9.2 per second. And we can look at the units for all of the Ks and see what order this reaction is, because that will help us determine which equation we need to use. So the reaction is first order, and you can keep a chart with you so you can see what the units are. Usually the question will tell you, okay, what order the reaction is, so you don't have to think about it too much and or memorize any of the units. It's fine. But in this case, it was not given, so we had to look at the chart. All right, so it is first order. And so what we do then is we find the equation for first order. Okay, and so we are supposed to figure out the concentration of A after time t. Initial is given to us. Okay, so this is the equation. We go ahead and plug in all the numbers. And so AT over A0, okay, and this ln is natural log, okay, which is not the same as log, okay, this is natural log, which you will find in your calculators as E. And this is equal to 9.2 over seconds, and that's the units, times seconds, okay, which is 1 time kt, right? So t then is 1 second over here, so which means that the natural log of final over initial is minus 9.2. So now what we have to do is we have to actually do the inverse of this log so that we can get rid of this natural log, and so we can get this back into our normal numbers. And so this is what you will do. Okay, for your calculator also, please learn how to use your calculator. Once you raise the natural log to the power of negative 9.2, don't forget the negative, to negative 9.2, then this is the number you will get. Okay, so now we are back in normal numbers. Once you're in the normal numbers, now you know the concentration of the initial starting material, so which is 6 molar, so you plug that in, and so the final concentration would be 1.01 times 10 to the negative 4 times 6 molar, and boom, Here we go. Okay, that is going to be our final answer then. So you can see that within 1 second, so much of cyclopropane has been gone. Okay, so much of it. 10 to the negative 4 is like 0.0006. Okay, so going from 6 molar to 0.0006. Okay, that is a lot of reaction happening in 1 second. Okay, and that has to do with the rate constant. This is what we calculated from the order of reaction. Okay, so once we know the order of reaction, then we can do all of this other stuff. So you can see how everything is connected. And then we have something which is called the half-life of a reaction. A half-life of a reaction is by the time or the time it takes for half of the reactants to be consumed. Okay, and so now what we'll do is we'll use the same equations that we had before with the integrated rate law, except the final concentration is going to be half of that of the initial concentration, because that's what half-life is. Okay, by the time half of your concentration is gone. All right, and so instead of 80, we will have half of A initial. Okay, and so for the first order reaction, this is the integrated rate law. And so then the half-life equation, after doing all the rearrangement and calculation, this is what it comes out to be. Okay, and so for a first order, this is what it comes out to be. I love the first order half-life, so easy. Okay, and then this is the second order, okay, where this is how it gets rearranged, okay, to be. So again, remember the AT is being substituted by half of the original concentration. Okay, and so that's why we can rearrange all of this, and you don't see the AT in there because you don't need it. Okay, you just need the initial concentration and some way to figure out how to get to the half-time. So here's an example of half-life. Ammonium nitrate is unstable, and because ammonium ion reacts with the nitrate ion to produce nitrogen, and this is what we have to give nitrogen and water. In a solution that is 10 molar ammonium ion, the reaction is first order in the nitrite. And the rate constant is given to us. What is the half-life of the reaction? Okay, again, you need to know your equations. You need to know that this is first order. Okay, so the rate is first order with nitrite. K is given to us as that. So for the first order of reactions, then this is how we would calculate. KT and a half is equal to 0.693. And so that means the time, okay, what is the half-life of the reaction? Half-life of the reaction T half is 0.693 divided by K. Easy calculation to do. Nothing much to it. So 3.9 minutes comes out to be the answer. This was given in seconds. Depending on what you're calculating and what the answers are given to you, if it's a multiple choice and you're supposed to leave it in seconds, leave it in seconds. Otherwise, convert it to minutes if you want to. It depends how the question is posed to you. But anyhow, simple calculation to do. Okay, and so this was a first order. And you could do the same thing if you had second or third order. You would just use the right equations for it. One of the nice things about doing the rates of reactions is that if you don't have certain things available to you, or you don't want to do calculations right away, then one of the easier way to tell the rate of reaction or the order of reaction without doing detailed calculation is by graphing them, okay, by taking whatever data you have and graph the data, okay, of change of concentration over time. So for example, if you're doing a rate of reaction study and you have a computer available to you along with something that you can take data with, like a pH meter or spectrophotometer, then you hook it up to a computer, and the computer collects all the data and then will graph it for you. And then so there are three possibilities given over here, one for zero, one for first and second order reaction. So for zero order reaction, if you plot the concentration of one of the reactants versus time, it's going to be linear. For a first order reaction, natural log of concentration of A versus time, that is linear. For a second order reaction, 1 over the concentration of A versus time, that is linear. Okay, so what happens is you take all your data and then you can start plotting it. So for example, you get the data, say, of a reactant nitrogen dioxide. Okay, and then you plot this and you think, okay, I have no idea, okay, what this is. So let me plot the data. Okay, so you plot the natural log of nitrogen dioxide concentration versus time, and this is what you get. And you're looking at this and you're thinking, okay, this does not look straight. Okay, so it's not a straight line graph. And so what you do then is you say, okay, let me change this a little bit. So when you plot it as 1 over nitrogen dioxide, you change the scale, then you get a straight line, okay, which means that once you get a linear line, then it means that your reaction is that order, which is second order in this case. So really you only have 3 options to work with, the 0, first, or second order, okay, and so you can plot 3 graphs and see which one is linear, and then how also you can predict what the overall order of reaction is, okay. And so this is really good if you have only one starting material. If you have 2, then you won't be able to figure out for individual unless you look at the concentration of individual reactants, but you can tell the overall reaction at least. So here is a little bit of a chart, okay, giving you everything that you needed to know about first and 0 and first, second order. The only thing it does not have is the units, okay, in which you can fill in the units of K yourself, all right, if you want to. So in any case, this is a table, very nice table. So 0 order, first order, second order, this is the rate law, this is the integrated rate law, we did the half-life also, and now the last column here tells you about the straight line plot, okay, what you should get. So for a 0 order, for example, it's concentration of A versus time, and the y-intercept that you have will give you the initial concentration of A. Okay, and here the graph will cross the origin, okay, which is a 0. So if you have first order reaction, for second order reaction, the y-intercept is different, okay, and so this table is a very useful table for that matter. So let's do a couple more calculations on how to calculate the concentration over a given time. So for example, in this one, the rate constant for a reaction is given to us, which is 7.5 times 10 to the negative 3 per second at 110. The reaction is first order with respect to A, which is great because anyhow, that's the only reactant there. How long in seconds will it take for A to decrease from 1.25 to 0.71? So the formula that we need for the first order reaction is right over here. So what we need to calculate now is actually for T, okay, for the time, which is seconds. So we'll get the 2 concentrations that we have. The final concentration is 0.71 and initial is 1.25. That is all equal to minus the 7.5 times 10 to the negative 3, which is the K per second, okay, then over here. And so then of course we can calculate T from the very straightforward kind of a calculation. The previous one that we did where we had to calculate the concentration, final concentration after a given time, was a little bit different because remember you have to take the anti-log, okay, of the log on both sides, all right. So this one is a little bit more straightforward. So here is another problem with calculating the concentration. Now in this case, the reaction is given to us also, which is I plus I is equal to I2. And this is a second order reaction which has a rate constant 7.0 times 10 to the power of 9, okay, at 23. So the question is, if the initial concentration of I is 0.086, then calculate the concentration of it after 2 minutes. So we have to use the integrated rate law for this one, and then we have a half-life to calculate also. So the half-life of a reaction when initial concentration is 0.6 and when it is 0.42, okay, so different concentrations to begin with. So the way to get this started is, of course, see what we need, and we need a second order rate equation. So the second order rate equation is this one, and all then you have to do is plug in your numbers because this doesn't even have any natural log or anything. And so plugging in our numbers here, 1 over the concentration, which is what we are trying to find out, calculate the concentration after 2 minutes. And so then K is this and T is 120, and remember to convert this into seconds because the rate is given to us in seconds. So this is seconds also, and then plus 1 over the initial concentration. So then it comes out to be this. And so then A is of course then the inverse of this, all right, which is 1.2 times 10 to the negative of 12. Okay, so that is how you would calculate the concentration over 2 minutes. And now we have to do the calculation for half-life. So half-life equation, again, remember we have to get for second order. And for second order, the half-life is 1 over K and then the initial concentration, which we have 2 half-lives to calculate depending on the concentration, 0.6 and 0.42. So calculate for both of them. K is the same, initial concentrations are different. Okay, and so here are the different half-lives, okay, for this one. So obviously you can see that the higher the concentration, the shorter the half-life, okay, which means that it's getting consumed faster. Okay, that's what's happening. And you have low concentration, it takes a longer time to get to the half-life. So nice calculation here for second order reactions. So here is what I would like you to know from this little portion of kinetics. You should be able to calculate the order of reactions. You should be able to calculate the concentrations of reactants at different times. Okay, so you have to know whether it's zero order, first order, second order. You should be able to calculate the half-life of reactions, or calculate how much concentration will be left after the half-life, whatever it is. Okay, and here are all the formulas that you need for this one. If I were you, I would just go ahead and plug in all the units also, okay, for K over here. So that's it.